and I've been working on this kernel implementation of the atomic page flip and mode setting stuff. So this is a rough picture of how the hardware generally looks like in the display controller. So we have two of these pipes, so the data flows through the pipe, gets scanned out by a bunch of planes on the other end from memory, and then it flows through the pipe and out some encoder and connector, whatever, in the end. And so this white stuff is the hardware basically, and the colored stuff is the software abstractions. So we have the DRM plane for the overlay planes, and the DRM CRTC, which currently covers the primary plane and the cursor plane as well. So that's kind of wrong, but that's what we have at the moment. And so the idea is to use the planes nicely. Okay, so let's say we have the primary plane that has the background picture with the picture frame, and then we have this picture of this dude here, and we want to use the overlay plane to, I guess, scale it and compose it into the picture frame, into the final image. And then we want to animate while using the overlay. So we want to, let's say this is some kind of animation of a museum or something, and we're panning the camera around the wall or something, so the picture should move like this. And then we get some problems with the current upstream code, because we don't do the flip and overlay movement in sync. So we can get one of these intermediate steps, or if we're lucky, we'll get the correct picture directly, but I don't trust in luck, so I want to fix it. Right, so a bit about the hardware. What's the problems with the hardware? So the hardware, usually the display control hardware, is using double buffered registers internally. So you would do MMIO writes to this first set, register file 1 here, and the hardware will actually internally use the copies of those values in this second register file. And it will only do copy the values from the register file 1 to the second one at the start of VBlank, which is kind of the square wave at the top is trying to represent the display scan cycle. So when it's low, we're in the active video portion, and when it's high, we're in the vertical blank period. And so this is, so here we try to write 3 registers, and then the hardware will latch them at the VBlank. And it looks nice in this case, no problem. But we get into problems when this happens. So we can try to write 3 registers, but we manage to write only 2, and then we hit the VBlank, and the third write happens after the start of the VBlank, which means that the 2 registers got latched in the first VBlank and the third one only in the one after that. So we get this. The second frame here will be corrupted somehow. Doesn't look nice. And so we have to fix that somehow. And this is kind of it. So my idea was to prevent register writes while we're too close to the start of the VBlank signal. So we had this kind of no-fly zone there. And then we delay the register writes slightly until we're safely past the danger point. And then we get the latching as a one atomic unit. And well, some hardware does have a bunch of features to sort of help here, but I think I've seen about 5 different variations of how that can be done, but I still haven't seen the correct one actually. So there are various problems with all the things I've seen different hardware engineers try. So we have to do the software tricks here to get it right. Okay, so a bit about the API stuff. I guess this is the pipe set part. So we currently the DRM API, we have three things that we are using. We have the page flip IOCTL for flipping the primary plane, CRTC. Then we have the update plane IOCTL for moving overlays and flipping them. And the third thing we have is the properties, which are like individual pieces of state that you can come up with. You can basically give them a name and attach them to a plane or a CRTC or a connector where they originated actually. So we could try to use these properties for the atomic stuff, and my idea here was to actually use exclusively properties. Because otherwise we would need to have some kind of maybe an array of these plane coordinates and everything in the IOCTL structure, and then we have some fixed size limits there, and it's not very flexible. So I just thought maybe make everything into a property and just have a like arbitrary list of properties in the API, the new update.
Plus with properties, if you did like YUV color conversion, you can update, color space coefficients or other random stuff with the flip to the new buffer.
Sorry.
You can do a lot more. Like, say you have some properties to control whether the YUV to RGB is, whether it's like full range or compressed range YUV or other things that you want to update at the same time you flip to a new.
Yeah. So you have lots of flexibility with properties. And so one idea I had was maybe to reuse the current API for the properties, which is just a set property IOCTL, I think it was called set property. And basically it allows you to set a single property for a single plane or a CRTC or connector. But then we would need to do some kind of transaction mechanism where we would start the transaction, set a bunch of properties, and then finally end the transaction and commit the state to the hardware. Or the other option is to come up with a totally new IOCTL, which allows you to like bulldoze the whole state into the kernel with one operation. And the transaction thingy has a bunch of problems, like if you have two threads trying to use the file descriptor at the same time, what happens? And then if you hook in a debugger or something while you have the transaction open, what should happen? No one else can use the device, or who knows. So it has a bunch of problems. And so I actually went for the bulldozer approach in my API. And this is kind of it. So the structure is basically 5 lists of stuff. So the first list contains the IDs of the objects, so these can be CRTCs or planes or connectors. And then for each of those we have the number of properties that we want to set. And then we have the list of properties, their IDs, and then the new values for them. And the property values are 64-bit integers, so that's not maybe enough in all cases. So I added an option of using these blob properties also. So a blob is just a bunch of bytes with a length. And currently it's only used for EDID data, so it's only read-only at the moment, but in my API it's also write. And I'm actually using the blobs currently to transfer the display mode, the timings for the display mode. Because splitting that up into individual properties would mean we'd get like a dozen new properties for each CRTC. And some other things, it could be used like for gamma tables or like CSC matrices or something like that. There's a bunch of uses that want to support. Right, so that's the outside view. And then in the kernel itself, I actually went for the transaction approach. So the kernel DRM core gets the IOCTL into the kernel, and then it will use this kind of transaction system. So the driver provides these function pointers that the core will call. So in the begin, the driver can allocate whatever it needs, like state tracking structures or something. And then for each property in the ioctl, the core will call the driver's set property function. And finally, the driver can check the full state, because we cannot really check that much at each set stage, because we don't know the final state of the system. So we have to have this separate check. And then if the check works out fine, then we can commit the state to hardware, which is where the vBlank magic happens then. And then in the end, the driver will free up whatever allocated as temporary storage and so on. So that's the internals. Alright, another API issue. This is kind of showing what the current page flip ioctl does. So the white boxes here are like page flip operations from user space. And then the colored boxes in the bottom try to show which color you will see on the screen at which time. And then the small colored box there is the new buffer basically that you want to flip to. So here we flip first to this red one, and then we get this page flip event back at vBlank time when the flip happens. And this is kind of okay. The page flip event doesn't really tell you that much. And it pretty much only works nicely if you render at less than the vertical refresh rate of the display. And I actually want to do something more. So this is kind of my new event system. It's a bit crowded here, but I'll try to explain it a bit. So here we have two planes actually, and we're flipping them at slightly different paces here. So the first thing I want to do is I want to attach to this event the buffer ID, basically the ID of the previous frame buffer. Or rather, not the previous one, but the one that is now available for rendering. So first we're scanning out from this gray buffer here, and then we do a flip to this red one. So nothing happens at that point, of course. That's the first flip. But then we want to flip, before the vBlank, we want to flip again to this green buffer. And now we notice that the red buffer is not used at all, so we can send out an event and telling the user land that okay, you can use this buffer again for rendering. And then we'll do the blue flip here, and then we notice how the green buffer is now available. No point in keeping it busy, keep it back. And then finally at the vBlank time we get the flip actually happens, so then we flip to the blue buffer, which was the last one flipped before vBlank. And then the event will carry the ID of the gray frame buffer, which is no longer being scanned out. So the buffers no longer rotate in this kind of strict order. They shuffle around depending on how fast you flip. And this allows you to render at 5,000 FPS without tearing or something, whatever you want. So it's nice for benchmarks, and maybe some gamers would like it. And then we had another use case actually, where we had two displays on a system. One was 60 Hertz, and then we attached like an external 30 Hertz or some slow display. And we had a cloned mode, so we didn't want to do any copies. And what I just did, I just basically flipped, throttled to the 60 Hertz, and I flipped both displays at each 60 Hertz interval. And then the external display would just randomly drop basically frames. But it would also get the last frame that was rendered all the time, so the latency was kind of minimized using that mechanism. So it has some uses. Yeah, and then the other thing I changed is that I send out events for each plane. So previously we just had the event for the whole CRTC for the page flip. But now, because I'm sending out the buffer ID in the event, I basically have to either have a variable length event which carries a list of buffer IDs, or I send out events for each plane individually, which is actually what I chose to do. So you get more events, but you can use it to track the buffers quite nicely actually. So that's about it. Okay, so let me say a few words about the mode setting side of the equation. And I decided that I want to do the page flip stuff and the mode set stuff at the same time, basically because the same API works for both cases. So in each case you want to basically just shuffle in an arbitrary chunk of data to the kernel and have it set it. Right. Okay, so let's look at the mode setting. What's the problem with mode setting in general using the current setcrt CI tool? So let's say we have a system here with two displays on a single graphics card, and let's say we have some kind of shared resource there with 3 N units available in total, and we start out with like a small display mode on each display, and so both require these N units of this resource now, and we'll check the constraint, it's fine. Then we want to change both displays to a higher resolution. So with the current API we have to do it in steps. So in the first step we'll change display number 1. And we'll check the constraint here again. Okay, it's still fine. We can do the mode set here. We'll blink the display off and back on with the new mode. And then we come to the second display. Oops, we can't do it. And now what we need to do is we need to roll back the first display to the original mode. So we need another blink there, which is not really nice at all. So if we just could see the full state in the beginning, we could check the constraint in the beginning and notice that, yeah, we can't do it, so we don't clobber the hardware state at all. That's the mode setting side of the equation. And internally it's kind of, well, most of the code is shared between the code paths here for the page flip and mode set. So all the state tracking and checking, that's shared. And only when you actually start to apply the state to the hardware, then I have two code paths. One is the atomic stuff and one is the blocking slow mode set path, because I guess no one wants to do asynchronous mode set support. That's kind of difficult. Alright, I think that's about it. I can maybe show a demo too. If this will cooperate. No. Okay, so this is my test application. So here the bigger triangle-ish object is rendered to the primary plane, and then the lighter background one is in the overlay plane. And now I can actually, well, I can animate it. So it's now rendering at about 200 frames per second, even though the refresh rate is something else. Well, I can actually throttle it and then I can see. So now it's throttled to the refresh rate, which is 60. Okay. But as you can see, hopefully, it's rendering at 200 frames per second. but there's no tearing at all. So it just props the older frames and slips to the last frame. If you managed to render to that period. Okay, and then I can stop it maybe. And now I will I'll disable the overlay for a while, and then I'll do a something. Yeah. Okay, so now I'm rendering this black box, the position directly beneath the overlay into the primary plane. And for the overlay, I'm actually not changing anything here, so it's still there. And now I'll do another change. I'll push the button. See this one. So now I actually render both surfaces using the same color, but I still have the black box under the overlay. But when I enable the overlay, you should see a solid color here, I guess. Can you see? Okay, so and then let me disable the overlay just once more, and then I'll change my benchmark to randomly throw it around the screen, basically. So it should, I guess you cannot see that. Then, that's bad. Well, anyways, I'll enable the overlay, and now you should see a solid gray without any black anywhere. So I'm just randomly moving around the overlay, and if the atomic stuff works, they will flip in sync, and you will never see the black stuff leaking out from anywhere. And it's still rendering at 200 something frames per second. 217. If I disable the overlay, and then you start to see the black stuff there. Okay, well, that's about it. Nothing else from my side. So there it's now doing its thing. Okay, that's it. Any questions?
So